And we are studying homomorphisms and isomorphisms. So we have groups G and G prime, and a function f that maps G into G prime. So we say f is a homomorphism so that's the key word if f of x times y is f of x times f of y for all x, y, and g. So here I take x, y, and g, x, y, and I can multiply them, and I get the element x, y. And then f takes this to f of x times y over in g prime. On the other hand, I could apply f to x and get f of x, and apply f to y, and I get f of y. Those are two elements in g prime. And if I multiply these two, I get exactly f of x, y. So somehow this is a function that preserves or respects the group structure. Here I've written the groups as multiplicative groups. For example, if these were additive groups, if g and g prime are additive, then we would write f of x plus y if f of x equals f of x plus f of y. If g is multiplicative and g prime is additive, we would write f of x times y. This is multiplication in g. And then I have f of x and f of y, they're over in g prime, and there the operation is plus. Or if g is additive and g prime is multiplicative, if I have x and y in g, I have to add them, and I can apply f to that. Meanwhile, f of x and f of y are in g prime, there the operation is multiplication. So depending on whether your groups are additive or multiplicative groups, we have these four equivalent ways to define a homomorphism. And we have lots of homomorphisms in mathematics, even in calculus. So here are two examples. Well, I actually call it pre-calculus because there's no calculus here. Suppose we take R to be the additive group of real numbers. And suppose I take R, all right, R greater than 0 to be the multiplicative group of positive real numbers, right? So if you have real numbers, you can add them and you get another number with the identity 0. If you have positive real numbers, you can multiply them and the identity is the number 1. And I have the function, I'll call it exp from R to the positive reals, defined by exp of x is e to the x. That's the function. It sends every real number to a positive real number. And if I take exp of x plus y, that's e to the x plus y. But by the rules for exponents, this is e to the x times e to the y. and e to the x is exp of x times exp of y. So this function is a homomorphism. Exponentiating is a homomorphism. Okay, so this is an additive group, and this is a multiplicative group. And we also have a function that you know very well from the multiplicative group of reals to the additive group of all real numbers, which is the logarithm, the natural log, defined by the log, well, of x log x is that log x. Just take the logarithm of a number. You can take the logarithm of any positive number and you get a number from 0 to infinity. And I claim this is a homomorphism. Why? Because the log of x times y is the log of x plus the log of y. So I have a group homomorphism from the reals to the positive reals, and a group homomorphism from the positive reals back to the reals. And in fact, each of these is the inverse of the other, because the first thing you learn about the exponential, or one of the first, is the exponential of the log of x, that's e to the log x, is x. And the log of the exponential of x is the log of e to the x, which is x. So each of these functions is an isomorphism, has an inverse. So two of the basic functions in math and calculus are group homomorphisms. If you look at the graph of these things, that's the graph of f of x equals e to the x. It sends the real numbers to the positive reals. And if I take g of x to be log x, that's defined for the positive reals. And it maps the positive reals onto all the reals. So these are very nice examples of homomorphisms of groups. And I want to prove properties of homomorphisms. I already proved last time the following theorem. Suppose we have homomorphisms, say f from g to g prime, and the homomorphism h from g prime to g double prime. So then the composite function h composed with f, which sends g to g double prime, is another homomorphism. Another basic property of a group homomorphism is the following. Suppose G is a group with identity element E, and G prime is a group with an identity element E prime. Let F from G to G prime be a homomorphism. Then the following properties hold. First of all, F of the identity in G is the identity in G prime. If I take F of X, take X in G, F of X is in G prime, the inverse of F of X is F of X inverse. And the third says that I can extend the definition of a homomorphism from products of two to products of any number of elements, if I take a product of n elements, x1 up to xn, this is f of x1, f of x2, up to f of xn. So these are three fundamental properties of homomorphisms. And the proofs, well, proofs shouldn't be too hard. Suppose I take E. So E is equal to E times E. So f of E is f of E times E. And because f's a homomorphism, this is f of E times f of E. If I multiply, I don't know what f of E is yet, but if I multiply by f of E inverse, I get f of E inverse is f of E, f of E, f of E inverse. F of E times f of E inverse, that's the inverse, that's the identity in G prime. And this is the identity in G prime. This is f of E times E prime, which is f of E, because this is the identity. So f of E is equal to E prime. So that is the very classical proof that a homomorphism maps the identity of one group to the identity in the other group. What about the property of inverses? So suppose I let x be in G, then x inverse is the identity. So f of the identity is f of x inverse. Of course, f of the identity E is E prime. And this is equal to f of x times f of x inverse, which means if I multiply f of x by this element, I get the identity, which means f of x inverse must be the inverse of f of x. Any questions about that? Then the last statement is simply an induction. We know that if I take a product of two elements, f of 1, f of x2, that's f of x1 times f of x2. So if I take a product of three elements, that's like f of x1, x2 times x3. So this times this. So this is f of x1, x2 times f of x3. But this is f of x1, f of x2 times f of x3. And it should be clear we can continue this by induction. If f of x1, x2 up to xn, a product of n elements in the group G, take their product, is f of x1, f of x2 up to f of xn. Then, if I take f of x1, x2, xn up to xn plus 1, so this is now a product of n plus 1 elements. This is f of x1 up to xn times f of xn plus 1. Just because I can look at this as a product of these two elements, and it's a homomorphism. And this is f of x1 up to f of xn times f of xn plus 1. So if the statement is true for n, it's true for n plus 1, and by induction, therefore, it's true for all n. Okay, any questions about this? I mean, in algebra, one studies algebraic structures like groups. And one wants to look at functions from one group to another that preserve or somehow respect the structure. This is true for any object in algebra, whether it's a group or something else. And the relevant functions in group theory are these things we call homomorphisms. And I'm going to prove many properties of homomorphisms because this is the central part of group theory for us. So in general, if you have groups G and G prime and a homomorphism between them, we know if you take the identity, that gets mapped to the identity in G prime. Now, it might happen that, in fact, there are other elements, and these all get mapped to the identity. So this set of elements is called the kernel of the homomorphism F. So the kernel of F it's all elements X and G that get mapped to the identity such that F of X is equal to E prime. Everything that gets sent to F of X. And we also have, of course, for any X, X gets mapped somewhere, some F of X. And we can look at everything in G prime that is the image of something in G. And that's called the image of F. So this is all Y in, or all X prime in G prime, such that X prime equals F of X for some X in G. So there are many properties of kernels and images that are fundamental. So let me start to prove some of them. In the notes, and this is sometimes written as, well, no, whatever, that's what it is. So in my notes, this is theorem 13, page 25. So kernel of F is a subgroup of G prime. And not only is it a subgroup of G, excuse me, it's a normal subgroup. And F is 1-to-1 if and only if the kernel of F consists of just one element, the identity. So theorem 13 in the notes has different parts. This is part 3. I don't have to prove them. Let me prove them in this order. Why is this true? Proof. That X, first of all, F of E is the identity and G is E prime. So E is in the kernel of F. Every homomorphism has the identity in its kernel. If X and Y are in the kernel of F, then F of X and F of Y equal the identity. So F of XY is F of X times F of Y. That's E times E, which is the identity. So XY in the kernel of F means x times y is in the kernel of f. So this kernel is closed under multiplication. And if x is in the kernel of f, f of x inverse, I just sort of proved that this is the inverse of f of x, but f of x is the identity, and the inverse of the identity is the identity. So if I put these statements together, this says that the kernel of f is a subgroup. So therefore, kernel of f is a subgroup of G. Suppose x is in the kernel of f and y is any element in G. So what I want to show is y inverse is in the kernel of f. That will show that the kernel of f is a normal subgroup. So f of y x y inverse is f of y, f of x, f of y inverse. But x is in the kernel. So this is the identity. This is f of y times the identity, f of y inverse. Multiplying by the identity doesn't change anything. This is f of y inverse, which is f of y inverse, which is f of e, which is e prime. So I just proved that for any element x in the kernel and any element y in the group, this conjugate is in the kernel. So kernel of f is a normal subgroup. Suppose the kernel of f consists of just the identity. If x and y are in G and f of x equals f of y, then f of x, f of y inverse is f of y inverse, which is the identity. But f of x, f of y inverse, this is f of x, y inverse. So x, y inverse is in the kernel, which is just the identity element. So x, y inverse equals the identity. Multiply on both sides by y, x equals y. So what I just showed is that if the kernel of a homomorphism is the identity, if x and y get mapped to the same thing, x and y are equal. So f is 1-to-1. So if the kernel is the identity, the homomorphism is 1-to-1. And what about the converse? Suppose f is 1-to-1. If x is in the kernel of f, then f of x is the identity. That's what it means to be in the kernel. But the identity is f of e. So e and x both get mapped to the identity. And if f is 1-to-1, there's only one element that gets mapped to any given element in G prime. So e equals x. So the only element in the kernel is the identity. Okay. What about the image? So we have G mapped to G prime by some function f, and sitting over here in G prime is the image of G, or the image of f. So the image of f is all elements x prime and G prime, such that x prime equals f of x for some x in G. So I claim image of f is a subgroup of G prime, and the image of f equals G prime if and only if f is onto. Well, why is the image of f a subgroup of G prime? First of all, the identity in G prime is f of e, so this is clearly in the image of f. The identity is the image, it's f of e. And if x prime and y prime are in G prime, then that means there exist elements x and y in G such that f of x equals x prime and f of y equals y prime, which means x prime y prime is f of x, f of y, but that's f of x, y. So the element x, y gets mapped to x prime, y prime. So x prime, y prime is in the image of f. So the image of f is closed under multiplication. And finally, if x prime is in G prime and f of x equals x prime, then f of x inverse, that's the inverse of f of x, that's the inverse of y prime. Sorry, it's the inverse of x prime. So if x prime is in G prime, if x prime is in the image of f, then x prime inverse is in the image of f, because x prime inverse is the image of f of x prime. Onto simply means that every element in G prime is in the image. So this is really, this statement is just a definition. To say f is onto means nothing more than that the image of f is all of G prime. Sorry, let's continue. Yeah. What else can we say? Yeah, let's stick with that. There's a little bit more in the notes that. So there is then the following statement about isomorphisms. Remember, a homomorphism F from G to G prime is an isomorphism if and only if F is one-to-one and onto, that's equivalent to saying there is an inverse function whenever you have a one-to-one and onto function or map from one set to another. There's an inverse, which takes the image back to the domain where you started. The inverse function is a homomorphism. And in fact, it's an isomorphism because the inverse is automatically one-to-one and onto. And another way of saying this is f from G to G prime is an isomorphism. Being one-to-one is the same as saying that the kernel of f is the identity, and being onto means the image of f is all of G prime. Let's see. Let's see if we can find some examples of homomorphisms. Well, I already gave the function f of x equals e to the x and f of x equals log x. This was from R to R positive, and this is from R positive to R. Those were two examples. We have the function f from z to z defined by f of x is m times x. So fix an integer m, just multiply by m. This is a homomorphism of additive groups because f of x plus y is m times x plus y. By distribution, this is mx plus my. This is f of x, and this is f of y. So this is a homomorphism of additive groups. We also have from the integers to the congruence classes mod m, a function, f of x, defined by f of x is the congruence class x plus mz. So again, f of x plus y is the congruence class of x plus y, which is the congruence class of x plus the congruence class of y. This is f of x plus f of y. This map is onto but not one-to-one. Because, for example, f of 0 and f of m both get mapped to the congruence class mz, because m plus mz is mz. It's not one-to-one. Suppose we have G to be a cyclic group of order n. So let's say this is a squared, a cubed, all the powers of a up to n minus first power, and order n means that a to the n is the identity. And suppose we let G prime be a cyclic group of order, I don't know, m. So let's say it's b squared, b cubed, up to b to the m minus 1. Actually, let's just stick with G, the cyclic group of order n. Suppose we let D divide n. So n is d times k or d times q for some q. Let f of x equal x to the d. So you take any element x in this group and you raise it to the dth power. So f of xy is xy to the d, which is x to the dy to the d. It's an abelian group. This is f of x times f of y. So raising something to the dth power, that's a homomorphism. What is the kernel? The kernel is all elements x in G such that f of x equals the identity. Let's try to figure out what that is. Write this down again. So G is the cyclic group of order n. So define a function f from the group to itself by f of x is x to the d. So for example, if x is a to the power I, then f of x, or f of a to the I, is a to the I to the power d, or a to the id. Suppose d divides n. So n is d times q for some q. So what are the kernel and the image of this homomorphism? So the kernel of f, it's all x in G such that f of x is the identity. That's the definition. So this is all, let's say, a to the I in G such that f of a to the I, which is a to the id, is the identity. A has order n. So this is the set of all a to the I in G such that n divides I times d. And we said is dq. So dq divides id means precisely that q divides I. And I is between 0 and n minus 1, which is qd minus 1. So what are the multiples of q between 0 and qd minus 1? This is all a to the I in g, where I is equal to 0 q, 2 times q, all the way up to d minus 1 times q. These are the integers I, such that n divides id. So this means we're looking at the set of elements e, a to the q, a to the 2q, up to a to the d minus 1 times q. So this is actually a cyclic group of order d, generated by a to the q. This is an interesting example, so I want to go into it, I think, now in more detail. Let's just take a very concrete case. Suppose I take n equal to 6, and G is the cyclic group of order 6. So a to the 6 is the identity. And suppose f of x is the function, f of x equals x squared. So here, n is 6, d is 2, q is 3, right? 6 is 2 times 3. So what is the kernel of f? It's all elements a to the I in G, such that f of a to the I is the identity, where I, this exponent, is between 0 and 5, right? These exponents go, the identity is a to the 0, from 0 up to 5. So this is all a to the I in G, such that a to the 2I is the identity, and I is between 0 and 5. But the powers of a that are the identity are the powers divisible by 6. This is all a to the I in G, such that 6 divides 2I. Six divides 2I is the same as saying 3 divides I. What numbers from 0 to 5 are divisible by 3? Just 0 and 3. So this is a to the 0 and a cubed, or e and a cubed. So the kernel of f is e and a cubed. The image of f is just the square of all the elements. E, a squared, a to the 4th. A cubed squared is the identity. A to the 4th squared is a to the 8th, which is 8 squared, and so forth. So the image is a subgroup of order 3. The kernel is a subgroup of order 2. It's called the kernel of F, K. So we showed that the kernel of a homomorphism is a normal subgroup. So we have the quotient group, G mod K. The index, which is the order of G mod K, is the order of G divided by the order of K. The order of G is 6. The order of K is 2. So they're going to be 3 cosets. So the index of G and K, which is the number of cosets, is 3. Remember, G is the 6 powers of A. K is just E and A cubed. So what are the left cosets? I have K, AK, and A squared K. Right? K is E and A cubed. AK, you multiply everything by A. A times E, A times A cubed. That's A and A to the 4th. The left coset A squared K is A squared E, A squared A cubed. That's A squared and A to the 5th. So these are the 3 cosets which partition this group into 3 pieces of the same size. Let's look at another example. Oh, let's look at one more thing. We also have the canonical homomorphism. Pi from G to the quotient group, defined by pi of x is xk. So you can think of it like this. Here is G, E, A squared, A cubed, A to the 4th, and A to the 5th. Here is G mod K, which consists of these 3 cosets. Pi of E is K. Pi of A is AK. Pi of A squared is A squared K. What is A cubed K? Well, K consists of E and A cubed. A cubed K also goes to K. A to the 4th A goes to AK. A to the 5th goes to A squared K. So this is sort of a picture that shows how this canonical homomorphism operates, sending elements to cosets. This is 1, 2, of course, and every coset has exactly 2 pre-images. There are 2 elements that map to each of these cosets, the 3 cosets, so that accounts for all 6 elements of the group. Let's look at another example. Suppose we have let's take G to be the cyclic group of order 9. So a squared up to a to the 8th. Actually, let me stick with a6. For the moment, cyclic group of order 6. And define f from the group to itself by f of x equals x to the 4th. Or equivalently, f of a is a to the 4. F of a to the I is a to the 4i. So let's just see what this, how this function works. So we have e goes to e to the 4th, which is e. A goes to a to the 4th. A squared goes to a to the 8th, which is a to the 6 plus 2. A to the 6 is the identity, so this is a squared. A cubed goes to a to the 4 times 3, which is 12, which is a to the 6 squared, which is e squared, which is e. A to the 4th goes to a to the 16th. 16 is 12 plus 4, a to the 12th times a to the 4th. A to the 12th is the identity. This is a to the 4th. And a to the 5th goes to a to the 20th, which is a to the 18 plus times a squared. And again, a to the 6 is the identity. So a to the 18, that's a to the 6 cubed, that's the identity. This is a squared. So here we have the group. Here we have the group again. And we have this function from G to itself. And E gets mapped to the identity. And A cubed gets mapped to the identity. A gets mapped to a to the 4th. And a to the 4th gets mapped to a to the 4th. A squared gets mapped to a squared, and a to the 5th also gets mapped to a squared. So just from looking at this picture, we can see that the kernel of f is e and a cubed. The image of f is e a squared and a to the 4th. Yeah. Very similar to, but not the same as, the function we looked at a moment ago. the cosets G mod K. So this is the kernel. And G mod K, again, consists of the three cosets K, AK, and A squared K. Any questions? This is all very basic group theory, not necessarily easy group theory, but basic group theory. So this, just recall, we have a group G, an element X in G, and we say X in G has order K if X to the K is the identity for some positive means greater than or equal to 1, positive integer K. X has infinite order. If it doesn't have finite order, which means X to the K is not the identity for all positive integers K. So for example, if again we take G to be the cyclic group of order 6, oh, sorry, an element X has order K if X to the K is E for some positive integer K, and K is the smallest such integer. So for example, E to the first power is E. So E has order 1. If we take A to the 6th is the identity, and no smaller power of A is the identity, so E has order 6. What about A squared? A squared cubed is the identity, so A squared has order 3. 3 is the smallest power of A squared, that's the identity. What about A to the 4th? Well, you have A to the 4th, A to the 8th, which is A squared. Cube it, you get A to the 12th, which is the identity. Oops, sorry, A cubed to the 4th. No, let me say this correctly. It always helps. A cubed, if I square it, I get the identity. So A cubed has order 2. A to the 4th, if I cube it, is A to the 12th, that's the identity. So A to the 4th has order 3. And A to the 5th, the smallest power of A to the 5th, that's the identity. I have to look for power multiples of 5 divisible by 6. 5, 10, 15, 20, 25, 30. The first time I get a power of 6 is A to the 5th to the 6th. So A to the 5th also has order 6. So this is a table of the orders of the elements in this cyclic group. Suppose I took G to be a cyclic group of order 5. Say the generator is B. So B to the 5 is the identity, and smaller powers of B are different. So E to the first power is E. So E has order 1. The smallest power of B, that's the identity, smallest positive power is B to the 5th. So B has order 5. What about B squared? If I take powers of B squared, the exponents are 2, 4, 6, 8, 10. That's the first time I get a multiple of 5. So B squared to the 5th is the identity. So B squared also has order 5. B cubed, the multiples of 3, 3, 6, 9, 12, 15. First multiple of 3, which is divisible by 5, is the 5th. So B cubed also has order 5. And B to the 4th, the first power of this, which is the identity, is also the 5th power. So in this cyclic group of order 5, the identity in every group has order 1, but every other element has order 5. That's kind of an interesting fact. So there's an interesting and important theorem, lemma, about orders of elements in cyclic groups. In the notes, this is lemma 15. So F from G to G prime is a homomorphism. So the first statement is, if X in G has order K, then F of X, which is an element in G prime, has order D for some divisor D of K. And second, if F is an isomorphism, not just a homomorphism, but an isomorphism, then F of X in G prime also has order K. So we can prove this result as follows. If X is in G and X to the K is the identity, then F of X to the kth power in G prime, that's F of X to the K, because the F's a homomorphism. This is F of E, which is E prime. So F of X to the K is the identity. And this means that the order of F of X is some divisor D of K. Because if an element raised to the kth power is the identity, the order of that element is a divisor of that exponent K. Suppose F is a is an isomorphism. What can we say then? Well, if f of x has order d, then f of x to the d is f of x to the d is the identity. So x to the d is in the kernel of f. That means x to the d is the identity, implies d, the smallest order power of x, which is the identity, is kth power. So if x to the d is the identity, then d is greater than or equal to k, so d equals k. So if f of x is order d, d has to be equal to k. All right, so I'm going through a lot of heavy group theory, and for everything I do, it takes time to learn it, and I really encourage you to spend as much time as you can with the notes going through trying to understand this. Let me make one last remark about group theory. It's nice to have examples of groups, and there's a way, given two groups, to construct a new group from it. So the G1 and G2 be groups. The product set G1 cross G2, this is all ordered pairs x and y, with x in G1 and y in G2. So this is a set of all ordered pairs. And we can define a multiplication in G1 cross G2 as follows. Maybe let me change this notation. Let me call this all ordered pairs x1 and x2, where x1 is in G1 and x2 is in G2. So if I have an ordered pair x1, x2, and another ordered pair y1, y2, I multiply them by multiplying coordinate-wise. x1 times y1, which makes sense because x1 and y1 both are in the group G1, comma x2, y2. So I just defined the multiplication on this product set. So I claim G1, G2 with this binary operation is a group. So it's clearly closed under this multiplication. What is the identity? The identity E would be the ordered pair consisting of the identity in G1 and the identity in G2. Because if I have x1, x2 times E1, E2, that's x1, E1, x2, E2, which is x1, x2. And E1, E2 times x1, x2 is E1, x1, E2, x2, which is x1, x2. So this is the identity. Associativity is as follows. If you have x1 x2 times y1, y2, and I multiply that by z1, z2. This is x1, y1, x2, y2 times z1, z2. This is x1, y1 times z1, x2, y2 times z2. But multiplication is associative in a group. So this is x1, y1, z1, and x2, y2, z2. And this is exactly x1, x2 times the product of y1, y2 times z1, z2. So this is exactly the associative rule. And the inverse of xy is x inverse, y inverse. So this product of groups is a group. And let's see if I can figure out one more interesting example. So the congruence class is mod 2. Contains two cosets, the even numbers and the odd numbers. Congruence class is mod 3. Consists of three cosets. The multiples of 3, the numbers that leave a remainder of 1 when you divide by 3, and the numbers that leave a remainder of 2 when you divide by 3. So let's say this is my group G1. This is my group G2. What is the direct product? This is a group which consists of ordered pairs of the form A plus 2z, comma, B plus 3z, where A is 0 or 1, and B 0, 1, and 2. So the order of this group, 2 times 3 is 6. This is a group with 6 elements. And the group operation is as follows. If you have A1 plus 2z, B1 plus 3z, you want to add it to another element of this form, A2 plus 2z, B2 plus 3z. That's equal to A1 plus A2 plus 2z, B1 plus B2 plus B3 plus 3z. That's a group. Now, another group with 6 elements is the integers mod 6. So this is everything in the form C plus 6z, where C is 0, 1, 2, 3, 4, or 5. And I'm going to show, but I think I'll wait until next week to show this. If I take the function from z mod 6z to z mod 2z times z mod 3z, define, so this is a group with 6 elements, and this product of two groups also has 6 elements. So define this by f of a plus 6z is equal to a plus 2z, a plus 3z. I claim that this is an isomorphism. Yep. All right, well, there is a considerable amount here to digest. It's in the textbook, the Dover paperback book, but it's in more detail and I think clearer by far in my notes. But this is your mission for the coming weekend, to study this. I have office hours Wednesday, today, tomorrow, and Friday, and you're welcome to log in and ask questions or ask for more explanations about anything you might have. I see that someone put a question in the chat about half an hour ago, but I don't see the chat when I am lecturing. So if you have a question, just unmute and ask. That's always the best thing to do. Okay. Okay. If nothing, we're done. If it stops raining, I hope it'll be a nice day. Okay. Bye all.